Morning. So, what I will be presenting with my friend Eldon today is regarding the vehicle engine under thermodynamics. Now, I will try to make it as simple as possible so that my audience is able to capture all the important points needed for us to understand regarding vehicle engine. Now, let us begin. So, first of all, is that regarding this thermodynamics, how does it relate to vehicle engine? Is that thermodynamics teaches us to relate about heat, about energy, how we can use all this to generate power, how it able to, for example, how it able to apply into real life situation like engines in cars. Now, the thing is, under vehicle engine, there are two types of engines. One that uses Otto cycle and another one that uses diesel cycle. What are the differences? Now, there are a bunch of differences regarding these two engines, but in simple words, as we know that when we go to the station to fill our engine, to fill our car, sometimes we go with, do I choose gasoline or do I choose diesel? Now, those are the main differences that we generally know. But here, we will learn deeper on the details and the differences that Otto and diesel cycle carries. So, let us begin with Otto cycle. Okay, now for Otto cycle is that we have two types of graphs, right? One is PV, which is the pressure and volume, and another one is TS, which is the temperature and entropy. So the thing is about Otto cycle is that it consists of four processes, them being isentropic compression, isochoric heat addition, isentropic expansion, and lastly is isochoric heat rejection. The thing about them is, what does it mean is that it will carry out all these four processes before it complete a cycle. Now, let me explain from the beginning. The first cycle, which process 1 to 2, which is isentropic compression. Now, this cycle begins with where the air-fuel mixture is compressed adiabatically. This means there is no heat exchange with the surrounding. As a result, the pressure and temperature of the mixture increase, but the entropy remains constant. For process number 2 and 3, process 2 to 3, heat is added at a constant volume. That is what we meant by isochoric, constant volume. This occurs during the ignition phase, right? Remember, this is one of the major differences when it comes to Otto and diesel, which is spark plug. In process 2, spark plug ignites the compressed air-fuel mixture, and the temperature and pressure rise significantly, but the volume remains constant. Process 3 to 4, isentropic expansion, what happens is that following the heat addition, the high pressure gases expand isentropically, right? This is the power stroke, where the expanding gases push the piston down, performing work on the surroundings. During this process, the temperature and pressure decrease. Remember that. In process 3 and 4, the temperature and pressure decrease, but the entropy remains constant, as we can see from the PV and TS graph. Lastly, process 4 to 1 is isochoric heat rejection, where finally heat is rejected at a constant volume, and this represents the exhaust phase, where the spent gases are expelled from the cylinder and the pressure and temperature drop, but the volume remain constant. That is literally the whole complete cycle of Otto cycle. Now, let us move on to the next cycle, which is diesel cycle. Now, for diesel cycle as well, in relation to Otto cycle as well, have four different processes. Them being isentropic compression, isobaric heat addition, isentropic expansion, last but not least, isochoric heat rejection. Also, described into two different diagrams, them being PV and TS, pressure, volume, and temperature entropy diagrams. So, I'll begin with the first process. The first process from 1 to 2 is isentropic compression. Now, what is this? This cycle begins with isentropic compression, where the air is compressed adiabatically, right? This means, again, there is no heat exchange with the surroundings. As a result, the pressure and temperature of the air increase, but the entropy remains constant. Now, for process 2 to 3 is isobaric heat addition. What happened? heat is added at constant pressure, and what will happen is fuel injection phase occurs. This is where diesel fuel is injected into the compressed hot air, igniting spontaneously. So the temperature increases significantly while the volume also increases. Process 3 to 4 is isentropic expansion. And what happened? Now what happened is that following the heat addition just now, the high pressure gases expand isentropically, and this is the power stroke where the expanding gases push the piston down, performing work on the surroundings. During this process, the temperature and pressure decrease, but the entropy remains constant. Last but not least, process 4 to 1 is isochoric heat rejection, and finally heat is rejected at a constant volume. This represents the exhaust phase, where the spent gases are expelled from the cylinder. The pressure and temperature drop, but the volume remains constant. Those are the 4 processes in diesel cycle. Basically saying we can learn them their differences respectively by knowing all these processes. Like as clear as the sky, what we can see is the existence of spark plug in this in Otto cycle, whereas there isn't in diesel cycle. But then the question now, how does diesel cycle work? Mostly using compression rather than spark plug that ignites the air fuel mixture. So that would be it for for my part in this presentation. Thank you.
The Otto and diesel cycles are two fundamental thermodynamic cycles used in internal combustion engine. They both describe the sequence of processes that convert chemical energy from fuel into mechanical work, but they operate differently, leading to variation in efficiency, performance, and application. So, what is the difference between Otto cycle and diesel cycles? For Otto cycles, it uses a spark plug to ignite the air-fuel mixture, and its compression ratio is typically lower than diesel engines, usually around 8 to 1 to 12 to 1. And the efficiency of Otto cycle is limited by the low compression ratio and the fact that not all the fuel energy is converted into useful work. So, Otto cycle is generally use gasoline oil, which is volatile and has a high octane rating to prevent knocking. So for diesel cycle, it relies on the heat generated by high compression to ignite the fuel, and it is typically higher than gasoline engines, usually around 14 to 1 to 25 to 1. For diesel cycle, its efficiency is generally higher than the Otto cycle due to the higher compression ratio and more complete combustion of fuel. And the fuel used is diesel fuel, which is less volatile and has a higher energy density but a lower certain rating than gasoline. So move to the importance of the thermodynamics, which is why we learn thermodynamics in applying in vehicle engine. For an intake phase, the air-fuel mixture, by learning thermodynamics, we can know the proper ratio of the air-fuel and help us in understanding the properties of gas or air and the vaporization of fuel. So we can also determine the amount of air that the engine can draw in it, as it is influenced by temperature and pressure. And we calculated it with the ideal gas law PV equals to nRT. To compression phase, we can know that the work done to compress the air-fuel mixture increases its temperature and pressure. We're applying the first law of thermodynamics. And also, we are dedicated to increase the compression ratios lead to the higher thermal efficiencies as described by the Carnot efficiency. Design the engine which maximizes compression without causing knocking. And For the power phase, the first law of thermodynamics explains how chemical energy is converted into thermal energy. The rapid increase in pressure pushed the piston down, converting thermal energy into mechanical work. This is described by the ideal gas law and the principle of the Otto or diesel cycle. And the thermodynamic efficiency of converting heat into work is determined by the thermodynamic cycle Otto or diesel and real-world losses like friction and heat dissipation. At exhaust phase, after the power stroke, the exhaust gases still contain significant thermal energy. The exhaust phase involves heat transfer principle as the gases are expelled from the cylinder. And according to the second law of thermodynamics, the entropy of the exhaust gas increase, indicating energy dissipation and loss of useful work. Understanding the thermodynamics of exhaust helps in designing catalytic converters and other emission control systems to reduce pollutants. Lastly, we know that all of the motion of compartment release heat. Hence, we need a cooling system to prevent the vehicle engine to overheat. The cooling system uses the principles of heat transfer, convection, and radiation to maintain optimal engine temperature. And the radiator operates as a heat exchanger where the hot coolant transfers heat to the surrounding air. The effectiveness of this process is governed by the laws of thermodynamics. So that's all from us about the daily application in thermodynamics. Thank you.